we've done a little bit with arc length in the past, so that wasn't all that new, but I guess that reparameterizing thing was. But the curvature is something a little different we haven't mentioned before. It's not too bad, though. And actually what we're going to use to kind of define our curvature is the unit tangent vector. So let me just draw a two-dimensional rendition here of a curve. If I start here and talk about my unit tangent vector, which is just the tangent vector, but 1 unit long, so let me just say it's that long. We've got that. All right, now if I go, let's say I go a certain arc length S here out, what changes about my unit tangent vector? Well, it's still 1 unit long, but what's changed? It's now at a different angle. The direction of it has changed. And then if I go out another S from there, well, that's still 1 unit long, the unit tangent vector is, but the direction has changed also. Well, what curvature does is describes that change of direction in your unit tangent vector. And so what the curvature is, it's the rate of change of the direction of, okay? That's what curvature is, okay? It's the rate of change of that direction. The unit tangent vector changes. And they'll use the Greek letter kappa, which I don't know when here's going to be my way to draw kappa. That's going to be our designation for curvature. So it's the rate at which the curvature changes. Well, how do we write that in some terminology here that we're kind of used to? Well, it's the rate of change of the magnitude with respect to the arc length. The rate of change of, it's going to be the magnitude of the rate of change of the unit tangent vector with respect to the arc length. So, you know, if I did a smaller s, you know, it's going to change a little differently, but it would be, you know, consistent to whatever arc length you choose. This would be consistent throughout for this particular curve. So that's what the curvature is. It just measures how quickly that direction changes. You know, if you had one that curved up quicker, then the curvature would be larger. So that's what this does. All right, now it's a little easier to compute though, because you know, there's a lot of formulas involved on that. It's a little easier to compute because most of our curves are in parameter with time if we have a formula for the curvature in terms of time t, or t. And so let's see if we can convert the curvature to in terms of t. And the way you do that, if basically we're just going to do this, we're going to take the unit tangent, divide by dt there, and then ds dt. So take when we just divide by dt, but it's, you know, the derivative with respect to time of both of those. The same thing, top and bottom, still equivalent. All right, well, what does this top thing, what is that? The derivative of the tangent vector with respect to time t. What's another name for that? The derivative of the time, the unit tangent vector is just t prime, right? That's the magnitude of the t prime, yeah. And then the magnitude of our ds dt, well, that's what we just defined in what we worked on just in the last segment there. Remember, the ds dt would be just the magnitude of the derivative vector. That's the way we basically define that. So, the curvature, kappa, is the magnitude of the tangent vector derivative divided by the magnitude of just the regular derivative vector. Which is still a little calculating, but not too bad. All right, so let's find the curvature of our helix. A cosine, oh sorry, no, this is just a circle. A cosine ti plus a sine tj. This is just a circle. That's just a circle with radius a, because that's just two-dimensional, if you will. So that's just a circle of radius a. Okay? All right. So for kappa, we need two things. We need the unit tangent vector magnitude, and then we need the magnitude of the derivative vector. So we have to start with the derivative vector here. What would the derivative vector be? Negative a sine t plus a cosine t, okay? And then the magnitude of that would be the square root of that squared, so that would be a squared sine squared, plus that squared, so that would be a squared cosine squared. Yeah, so we're going to get the square root of a squared, the sine squared plus the cosine squared, after you factor off the sine squared, factor off the a squared. That would just be 1. So yeah, the magnitude there is just a of the derivative vector. All right, what about the unit tangent vector? It's the derivative vector divided by the magnitude of the derivative vector. Yes. That would be a cosine ti plus a sine tj. Whoops. Sorry. Yep. The a's are going to cancel. It's this one. I did the original one first. So we take that and divide it by magnitude, so we divide that by a, so yeah, the a's go out, so we have negative sine t I plus cosine tj. But for the curvature, we need the magnitude. That's our tangent vector. We need the magnitude of the tangent vector. So we take that and square it. So it'll be sine squared plus cosine squared. So yeah, that's just 1. So our curvature turns out to be 1 over a for a circle. So it's 1 divided by the radius, which the book points out there, that's just intuitive, because if you have a small circle, the a here, pretty small, say it's a half, that's going to mean, relatively speaking, large curvature, because you have the curvature, let's say it's a half, that's going to be 2. But if you have a larger circle, like 4, the curvature is just 1/4. So remember, that's the change, how it's changing. The direction is changing based on the arc length. So, yeah. So, going out further from one point to another, you got less curvature than that same kind of arc length down here. It's much more curvy, right? So, makes sense. Huh?
What would you measure curvature? It'd be like
Units? You're talking about the units?
Yeah, like
Units of curvature?
velocity
I hadn't thought about that. Let's see. So I think it's just units. I mean, two units, because if you think about it, those are just the units of that would cancel out, right? So it's just, yeah, it's just a number. Larger kappas mean more curvature. All right. Let's see. I'm trying to think. I want to do another one of those, or we got time, don't we?
But on a curve, just whatever given space, that curvature changes a lot.
Huh? Yeah. Yes.
Whereas in a circle, it's constant.
It's a constant. That's right. Yeah. Maybe that's why. Let's see. Let's see. Yeah, let's do the twisted cubic. Let's do the curvature for t . 1/2 t squared t squared. All right, so what's our derivative vector there? 1, comma, t, 2t. So our magnitude there (1 plus t squared plus 4t squared). So that's 1 plus 5t squared. Square root of that. Which makes our unit tangent vector then our derivative vector divided by the magnitude. Okay, so that would be 1 t 2t, and then we divide it by the square root of 1 plus whatever 5 plus 5t squared would be. That's right. Not a whole lot of simplifying going to happen there, is it? The magnitude of that then would be that divided by that squared. Which looks bad, but you know it works out pretty nicely because you're going to square that and then you're going to do the square root. So I'll show you what happens. So that'll be t squared over 1 plus 5t squared squared. And then this would be 4t squared over the square root of that squared. All right. So what happens on that? All of them have the square root, this square root squared, which cancels the square roots, but we've got it square rooted again. Okay. So basically what it amounts to is you've got that 1 over that again, right? And this will be 1 t squared plus, sorry, 1 plus 5t squared. Oh, how about that? Comes out to be 1 again. I guess that's why they chose these values again. Those cancel out. So our curvature then is the unit tangent vector derivative length divided by our magnitude of the derivative vector. And so that's 1 over, that's 1. That is the square root of 1 plus 5t squared. Okay. And so this one, yeah, this one's a little different than the circle because it's dependent on the t. Yeah, it does depend on the t. So that one's going to change curvature just by where you are on the.
So somebody might look at differences between curvature between
Mm-hmm. Yeah. How curvy is it at this place and this place? So yeah. Negative curvature? Yeah, because of the way it's defined there, I don't believe so, because you're doing the square roots of.
Yeah, it wouldn't matter.
Yeah. All right. Okay, so I've got time here for. Our unit normal vector. Okay, so here's what we're going to do. As we know, at a point, we have our unit tangent vector. And we talked way back, calculus 1, probably. Yeah, it's calculus 1. We talked about the normal vector, or the normal line, yeah. Well, now we're going to talk about the unit normal vector, which is going to be perpendicular to the unit tangent vector. And it's going to be, also going to want it to be 1 unit long as well. It turns out it's actually a pretty nice, easy, once you have the unit tangent vector anyway. Not too bad of a calculation. It turns out it's the derivative of the tangent vector divided by the magnitude to make it unitized, I guess. Yeah, it turns out that derivative of the tangent vector is perpendicular to the tangent vector itself. It's orthogonal. T prime, that vector, is orthogonal. If you look at the dot products, if you took the dot product of the t and t prime, it's 0. So since that dot product is always 0, they are orthogonal. So yeah, so it's just the derivative of the tangent vector divided by the magnitude of the tangent vector. So it turns out that that is one possible orthogonal vector. Because there's many. Yeah, there's many, because you're talking about 3 dimensions. You don't have to just deal with the plane. You can go this way, this way. Yeah. As a matter of fact, the book mentions the binormal vector, which is it's perpendicular to both, which means it's a cross product. Do the cross product of the tangent and the normal vector. And so in this case, that one would be coming out of the board. But all right, so let's find, let's do our helix here. Find the normal vector for unit normal vector. For our helix vector. Cosine t, sine t, t. All right, so for the normal vector, we need the tangent vector, which for the tangent vector, we need the derivative vector, yeah. So that's our negative sine t, cosine t, 1. And then the magnitude is also needed here, so that's already established that a couple times here, but it's the square root of 2, yeah. And so our unit tangent vector would be negative sine t, cosine t, 1, divided by the square root of 2. So the magnitude, I don't need that yet, do I? What I do need, though, is the derivative of that. I'll do too much here. Not too hard, yeah. It's just 1 over the square root of 2. That's just a constant, so we just have to do the derivative of that, right? Negative cosine, negative sine, and 0. And so then the magnitude of that we do need. Yeah. Just going to be 1, isn't it? That part's going to be 1 because that's cosine squared plus sine squared. Of course, this one just kind of comes along. Whatever the magnitude of that, multiply it by that, right? So I could put it in there, but it's just going to come. I guess I could have done that one earlier. That's just 1, isn't it? It's 1 over square root of 2. And so our unit normal vector then would be the derivative vector, 1 over the square root of 2, negative cosine t, negative sine t 0, and then divide that by the magnitude of the unit tangent vector derivative, which is 1 over the square root of 2. Hey, how about that? So it's just the derivative vector, yeah, in this case. Yep. So it turns out that was already 1 unit long. So, well, actually, it's not quite the derivative vector, is it? Because it doesn't have the square root of 1 over square root of 2. All right.